Good evening, Internet. I am Matt Buyak, and in this video, I'll be looking at the 9th problem from the Project Euler problem archive. So this problem asks us to find natural numbers a, b, and c such that a squared plus b squared equals c squared. That is, a, b, and c form a Pythagorean triple. In addition, it requires that a, b, and c sum to 1,000, and it asks us to find the product of a, b, and c. We'll note that it indicates that there exists only one such Pythagorean triple. So in the previous video, we looked at a technique for generating Pythagorean triples. And in the next video, we'll use that technique to solve this problem using analysis alone. But for this video, I want to take a programming-only approach and not take advantage of that technique. And while the algorithm that we're going to use is not going to be particularly deep, it will give us a chance to show some programming techniques to make your programs more efficient. And so let's get right into it. As usual, we'll copy our template directory to make our problem directory. And we'll open up our main.cpp. See, we'll probably need A, B, and C. And so before we get started, the most basic algorithm you could think of to try to tackle this problem is going to basically just search blindly over values of A, B, and C and try to find a triple that matches our conditions. And this is usually referred to as a brute force approach. But there are a few observations we can make to make our problem a little bit more tractable. The first is that we don't actually have to search over all three values. Once we have value of A and B, we can square A, square B, add the two, take the square root, and we have our value of C. And we can check to see if that's an integer, to see if it's a Pythagorean triple. We can add A, B, and C then to see if they sum to 1,000, and in that way check to see if we've found a solution. The other observation that we can make is that because A, B, and C are natural numbers, that is, they're greater than 0, and their sum is 1,000, we know that none of these can be greater than 1,000. They all have to be less than 1,000. So we might begin by searching over values of A, starting at 1 and going up to 1,000. And likewise, we might start with B equals 1 and also searching up to 1,000. Now, as we look at this solution, I'm going to introduce this variable called loop count. And this isn't going to help us solve the problem. It's just going to help us keep track of how many times we execute this innermost loop. And that'll give us an idea of how efficient our search is. The more loops we have to complete in order to find our solution, the less efficient our search is. So here we'll just increment our loop count. Okay, so now we can check. Let's see, we'll say uint 32t square root of a times a plus b times b. Likely have to convert that to a floating point value. That is a non-integer value. And we'll just assign that to c. And then we can check if a times a plus b times b is equal to c times c. and a plus b plus c is equal to 1,000, then we've found our solution. And so what we'll do is just create these variables, capital A, capital B, and capital C, which will keep track of our solution here. So normally what we might want to do when we find our solution, especially if we're only searching for a single solution, in this case we've been told that there's exactly one solution, we might just want to stop at that point since we know we don't have to search any farther. But what we really want to do is measure the total size of our search space. And if we stop early, we won't know what that is. It might be that we get lucky and we find our solution very early in our search, but that won't really tell us how efficient our search is. And so we want to continue even though we found our answer, just so that we can evaluate how efficient our approach is and see how the techniques that I'm going to show you improve the efficiency of the search. That is, they decrease the total loop count here. One thing to note is that this function, square root, will have to include, I believe, math.h in order to use that method. So at the end here, we will just print. We'll say capital A equals %u, capital B equals %u, capital C equals %u, A, B, C. And then we'll say loop count %u. All right, and run our solver. Okay, so we can see here we have A equals 375, B equals 200, and C equals 425. So we can check real quick if that actually is a solution. Presumably it is. So we have 375 plus 200 plus 425 does indeed sum to 1,000. And then we can try 375 squared plus 200 squared, and then we take the square root, and we get 425. So our program works. We have found our solution. And we could stop at that point, but we wouldn't have learned anything. So you'll see here the loop count is just shy of 1,000,000, 998,000 there. And so we'll see if we can find some techniques for improving the efficiency of our search. So the first thing that we might notice is that A and B are symmetric in this equation, a squared plus b squared equals c squared. That is, we could take our values in our solution over here and for A and B and swap them, and we would still have a solution. But you'll notice here that that means that we're searching both of those possibilities, and we really only need to be searching one of them. In fact, if you look at the original problem statement, it even suggests that A is strictly less than B. And so we can actually change our program to reflect that. So we can just say, let's let B is equal to A, rather than starting at 1. Yeah, that should work just fine. Okay, so you see that already we've significantly reduced the size of our search space. We get the same solution, or rather an equivalent solution, but our loop count has been reduced substantially. So the next thing that we could consider is that A can't actually go all the way up to 1,000. You can imagine if A is equal to 998, then you would have maybe A equals 1, or excuse me, B equals 1 and C equals 1. But B and C both have to be greater than A. And so that's obviously not a valid, or won't be a valid solution. And so we can reduce this range to get a smaller search space. And in particular, you might note that because B is at least as large as A and C is at least as large as B, and their sum is less than 1,000, we have 3A is less than 1,000. So you could see if we had A is equal to 333, B equals 333, and C equals 334, that would meet the requirements. But A could be no larger than that. And so we can change this to 334. And again, reduce the size of our search space substantially. So the next thing we might try to do, we looked at this bound on A and looked at how we might reduce that. But now we can do something similar with the bound on B. So again, we know that A plus B plus C is equal to 1,000. And so we know that because C is greater than B, we know that A plus B plus 1 is less than 1,000. That is, C is at least as large as B plus 1. And so we can write A plus 2 times B plus 1 is less than or equal to 1,000. But we can clean this up a little bit. If we subtract 1 from both sides, then we get less than or equal to 999. Or we can remove this equal and make it just strictly less than 1,000, and that is equivalent. And one thing I'll note is that this A plus 2 times B, you could write it as 2 times B, or B plus B, or even B left shift 1. And it's not entirely clear which of those is going to be more optimal. Often you'll see claims from programmers saying that one of these is optimizations like this, saying that a particular operator is faster than another. But for the most part, with something like this, the compiler is going to be able to figure out which one is best much better than you are. And so at that point, what really matters is what's going to make your code the most legible. And so we'll stick with A plus 2 times B here. And again, we can run our problem, and we see that we've made even more progress in reducing the total size of our search space. You'll recall that when we started off here, our search space was almost 1 million. And now we're down to 83,000. So obviously in this case it doesn't make much of a difference because our program is so quick, and our search space is still, even 1 million is relatively small. And so it finishes very quickly. But you could imagine if we were searching something where our inner loop was doing much more work, or our search space to start was substantially larger, that these are the sorts of optimizations that could end up saving you significant time waiting for your results. So the next thing that we can do, this isn't exactly, or it won't reduce the size of our search space, but this square root function is actually quite inefficient, and we can actually get rid of it. Earlier, you may recall me saying that it probably doesn't matter whether here we say B plus B or 2 times B, because the compiler will take care of it. But one place where it does make a difference potentially in which operators you use is that there is a sort of a hierarchy when you're looking at different arithmetic operations in terms of which are going to be more efficient. And sometimes in certain situations, the compiler will be smart enough to make transformations between them to make your code more efficient, but you shouldn't necessarily count on it. So in particular, addition is usually more efficient than multiplication, which is generally more efficient than division. And then in addition to that, operations on integers are usually significantly more efficient than operations on non-integer values. And then at the extreme end of inefficiency, you have operations like this square root function, where not only is it doing operations on floating point numbers, it's not even one of the primitive addition, subtraction, multiplication, division, one of the primitive operators. And so this is going to be potentially very inefficient. And fortunately, there's a way that we can remove it. So in particular, we have another equation for C. We can say C is equal to 1,000 minus A minus B. And just get rid of that square root altogether. Now, one thing you'll note is that we have to be a little bit careful because C is an unsigned variable. If A plus B were larger than 1,000, then this could potentially cause an underflow. And then we would end up essentially with a garbage value in C, which could cause our program to return erroneous results. But fortunately, because of our tightened bound on this for loop here, we don't have to worry about that. We know that A plus B is going to be less than 1,000. And so let's just double check. We don't expect that our search has become any more efficient in terms of loop count, but you can see it's exactly the same, but we've eliminated that square root. And so that's going to make our program faster, even if we're searching over the same number of iterations. Okay, so the last thing that we can do to improve our program is that this bound is still not quite as tight as it could be. And you could see that, for example, if we had a situation where A plus 2 times B was just less than 1,000, you would be getting values of C that were actually less than A and B, which is not allowed. And so we really, for this condition here, we want our check to be A squared plus B squared is less than C squared. That's the check that we really want to be making, because that's what we're looking for. But we don't actually have our value of C until we get into the loop here. And so we're going to have to restructure things a bit in order to be able to make that check the way we want. And so in particular, I'm going to start by changing this for loop to be a while loop instead. And so that's just moving this condition out here, moving this condition down here, and then changing this from for to while. And so now what that lets us do is we can calculate C here instead. And again, because of our condition in tightening this bound, we don't have to worry about negative or getting negative values here. What we do have to worry about, however, is now that we're calculating C outside of this loop, we'll need to calculate it, or we'll need to update it at the end of this loop here. So you'll notice that whenever B is incremented, then necessarily C will have to be decremented. And so now that we have our C calculated here, we can change this condition to what we really want, which is A times A plus B times B is less than C times C. Oh, excuse me. This should be less than or equal to. Otherwise, we won't get our solution there. And you'll see again we've reduced farther the total size of our search space. Now there's one more improvement we can make to this code. You'll notice that we're performing this check now in two places. Here we're checking to see if a squared plus b squared is less than or equal to c squared, and then we're basically doing the same check down here. And in fact, this check here has also now become redundant. You can see we're calculating C directly from that statement, and so it's guaranteed to be true. So there are a few more transformations that we can make to farther clean up our code. And in particular, we can make this while loop execute as long as a squared plus b squared is less than c squared. And then we can move this check outside of the main loop. So this should let us loop very efficiently to the first value of b such that a squared plus b squared is not less than c squared. And then we can check to see if that is a solution. So this doesn't actually improve our search count by very much, by 1 as you can see. But it does mean that some of those redundant checks that we were making before we're no longer making. And so our program has been made more efficient once again. So now, you might recall quite a while ago, we actually arrived at a solution. So now let's go ahead and check to see if that solution is in fact correct as reported by the archive. So if we do 200 times 375 times 425, we get this number. As you recall, the actual solution that it's asking for is the product of those three numbers. And so now if we go to the archive, we'll see that it indeed matches 31,875,000, and that is our answer. So as I said, in the next video, we will tackle the same problem using analysis only and the technique for generating Pythagorean triples that we looked at last time. So if that interests you, check that out.